So because we want something unconditional, there's no hope of trying to get a strong exponent of distribution, because that would tell you something about the Riemann hypothesis that we don't know today. So we try to necessarily do the same type of averages as in Bombier-Vinogradov. And in fact, one has to restrict these averages in various ways, because there's no known really complete analog of Bombier-Vinogradov beyond square root of x. So let me give two motivations quickly for this. Actually, I guess I can give three. So one is curiosity. There's a natural boundary which is square root of x that arises from Bombier-Vinogradov, which is actually a natural boundary for exponents of distribution for a very, very large class of arithmetic functions. So it's natural to try and see if we could go beyond that. Second motivation, one of the first applications of this was to the Titchmarsh divisor problem. So I remind you that this was the problem of studying the sum of the divisor function at p minus 1 when p is less than x. Okay, p minus 1 could be p plus any fixed constant, of course. So I told you, and I think you saw in an exercise, and nowadays it's really easy, that if you know the Bombier-Vinogradov theorem and the Boole-Titchmarsh inequality, you're going to see that this is some constant times x plus big O of, well, let's say x over log x maybe. And this you compare with, we interpret this, one compares that with just the asymptotic formula for divisor function without restriction on n being a prime or p minus 1. And here there's something which is quite a bit different. There's a two-step asymptotic formula. Okay, so the application of Dirichlet's hyperbola method gives an asymptotic formula with two steps, or applying Perron's formula to zeta of s squared gives you naturally two steps, because zeta of s squared has a double pole, which is where you have first a log x and then an x. And now if you compare, you might say, well, if really the other term is just big O of log x and cannot be made more precise, this would show a difference between these two behaviors. So here we have a nice asymptotic formula with two terms and then quite a bit smaller term. Here we would have just one. Now if you just apply Bombier-Vinogradov and Boole-Titchmarsh, you will not be able to get better than that. Or at least nobody has been able to get better than that. But if you use using exponential distribution beyond 1/2, okay, so one can get a two-term asymptotic formula. For the Titchmarsh divisor problems. Okay, so this was done, I think, independently by Fouvry and maybe Bombier-Friedlander-Ivagnette. But I would have to check this. So that's one motivation. Now, second motivation is the one that's the motivation for Zhang, but this is a type of motivation that existed already in the 80s when Fouvry and Ivagnette started working on such things. And in the original GPY method, so this was a crucial issue. So original Hildery method. Okay, so I will spend a few minutes to recall this method. So it's a simpler version of what James described. I'll go back to this simpler version since with the new method, with multivariable type of survoxive, it's not a problem to, I mean, there's no particular point in emphasizing the original, but here to motivate this work of Zhang, it's actually useful to go back to what Goldson, Pintz, and Yildirim were doing. So what they did was the following. So they constructed kind of Selberg-like sieve weights lambda d defined for d less than some capital R, such that we have some kind of nice lower bound for the expression that tries to count how many shifted tuples for an admissible tuple contain at least one prime, which had the following shape. This is probably going to be a bit too wet. I'll erase both and use the source one for the moment. Okay, and so the lower bound looks like that. So you sum over integers in some interval of length x. Then there's the sieve weights, which are built using the lambda d's, which are always bounded by d up to r. Then d divides the product of the n plus hi's. So here we have fixed some parameter k and an unmissable k tuple h1 up to hk. Then there's the square that makes this non-negative to avoid problems. And then you want to count how many of the n plus hi are primes. So this should really be some kind of characteristic functions of the primes, but for my purpose it doesn't make any difference. And you want to say that at least one is prime, and this would be the case if this sum is non-negative, because this is at most log of 2x plus a constant. So if this is strictly positive, there has to be at least 2 primes. I said 1 prime, but of course you need at least 2 to get bounded gaps. Okay? And so what did they get? So this is exactly the type of expression that James was dealing with, except that he had a more refined version of the sieve weights here, and that allowed him to actually try to do it even with a multiple of log x instead of just 12 or 1 here. Okay, and what is the outcome of the original GPY method? It would be an inequality like this. So there's going to be some theta, which of course will be an exponent of distribution of some kind. Then there's actually a second parameter, L, which comes in the choice of the weights. And in the original version, you get precisely that. So theta times k times 2l plus 1. So L is a parameter that's completely at your disposal, divided by L plus 1, k plus 2l plus 1. This would be the thing that comes out of the analysis of the von Neumann functions. And from the second term, you would get minus 1. This would be times x log x, roughly speaking. Sorry. Plus an error term. Okay, I'll put this error term in another location because that's what I want to analyze further. So the error term, roughly speaking, again, this will be very similar to things that James described. So you have moduli up to x to the theta. They are certainly square free, the way the thing is constructed. Then you have maybe some divisor function, so whatever capital M, let's say, of Q. Then some power of log maybe, M2, let's say. And the main thing is the error term in the prime number theorem. So delta, the discrepancy for lambda for x, Q QA, and you have the maximum. Okay, so now if we want to analyze what happens, okay, so this is an exponent of distribution in the Bombieri-Vinogradov sense. So theta is an exponent of distribution for the von Mangold function. So we know we can take theta essentially 1/2. So let's look at the size of the first term. So of course we want this to be as large as possible so that we can subtract 1. If we think of the numerator and denominator, you see that if L goes to infinity and K also, but L is kind of smaller order of magnitude, maybe square root of K, then you have something like 2 times KL. And this is divided by K times L. So you have a 2 here, you have 2 theta minus 1. And so this is only positive if theta is larger. So even theta equals 1/2 doesn't work. So then we need theta larger than 1/2 to get strictly positive main term, which is the goal, to get bounded gaps. Note in passing, I won't really comment on that, that even if you add the best possible theta, which is theta equals 1, you cannot control integers in isolate progressions where the modulus is larger than the length. You could not replace the 1 by 2. So that's in passing. That's one of the key advantages of the method of James, that it could take anything here. Okay, but of course, theta equals 1/2 is what Bombieri-Vinogradov gives, or even what the general Riemann hypothesis gives. So that was kind of very satisfactory at the time because we know 1/2 is a barrier and we see it appearing naturally. So it was very tempting to think that one could not improve the main term because of that. And of course that was a big mistake. Okay. So what James did, as you've heard also, independently Tao, what they did was they improved the main term by better choices of the weights. And this is what I'm going to not talk about, since we already saw James's exposition of that. So by making this choice of weights more delicate, but much more powerful, they could improve the main term and say that, in fact, not even theta equals 1/2 is needed, but just anything strictly positive would suffice not only to get bounded gaps, but even with theta equals 1/10 billion billions, you could still get here with 1 replaced by an arbitrary. Okay? But before that, there was the work of Jean. And so he worked on the error term and tried to get a better bound for this error term, essentially. So he improved error term. Right. That's where I must be very careful about this language. Remainder term. Okay. So there's a number of things that go into this. So I'll first describe, I already stated the theorem last week, but I'll remind you again of what is the variant that they actually proved. There's some work to be done to check that this variant is sufficient, but it's not so impossible. So I guess I'll at least erase one of these to have it ready when I'm done on the side. Okay, so I think this I can now hide because there's no problem. I mean, I don't want it right now. So more precisely, So there's a number of things that needs to be done. So first of all, and here I guess the way I define things I should first put the maximum. So that's the most naive way to write things. So first of all, if you remember the proof of James, that's just a generalization of this, so you can look at your notes and see how this type of error term arose. You don't need an absolute value. I mean, of course, if you can bound with the absolute value, you're in good shape, but you don't actually need it, the way the thing comes out. But then maybe you need something a bit more precise than just estimate, but that's not the problem. You just have some maybe unknown arithmetic functions, but of sizes that you control. You don't need the maximum over all residue classes. So you don't need quite absolute value of delta lambda. You don't need all A mod Q, co-prime with Q, but only those which are roots of this polynomial, this function of n which arises here, modulo A such that h1 mod Q. And so typically this will be, because Q is square free, this will be just k to the power the number of divisors of Q. So if Q is a prime and large enough, then the HIs are distinct mod Q, so you get exactly k roots, and for every prime you get k different roots, and Chinese who made the theorem doesn't get that way. So that's k to the omega of Q, which is certainly less than Q to the epsilon for any positive epsilon of such a. So that's quite nice, in the sense that, as I'll explain later, this number is not out of reach of type of techniques that were available to Zhang, but we don't know where these A's are. They could be located anywhere, so we cannot say that A is small. So if all the A's had been as small as the number of them, that would be much better. Okay. And the third thing is much less obvious. So the fact that you can take A to be that just follows from the method immediately. Much less obvious is that you can assume that Q runs over smooth numbers, so more precisely arbitrary fiber numbers. Always square free. Right? So this is not obvious. This is the type of thing that experts in field theory were kind of aware of, and that suddenly was explicitly noticed by Motohashi and Pins a few years after GP1 came out, although they couldn't exploit that observation. So if you remember, you can kind of have a very vague guess that something like this might be true. If you remember the way the thing came, the Q is not really a fixed Q. It's always going to be the least common multiple of two of these R's in the cell box C. So this Q will always have at least one factorization. And now if you could arrange a factorization to have many prime factors and so on, you could hope to get something like that. So if you just take this naive observation of cell box C, you just know you have one factorization, and you could try and exploit the two variables R1 and R2. Typically this is not flexible enough, but at least it exists. Okay?